So for this third video, we're going to focus on the shear deformation. And we're going to look at three types of shears. We're looking at the XY shear, the YZ shear, and the XZ shear. And we're going to use a pure shear specification as against a simple shear deformation. So let's sit back and relax as we get into this video. If you want to see how this has actually been done, I've made a video which shows how you build up this assembly to generate this virtual domain, and the second one talks about how to actually apply uniaxial deformation on the system. For this video, we want to create the shear stress cases. So the first thing, in terms of getting the XY pure shear deformation, we're going to hold the system securely at the back. So that means we're fixing it in the Y and Z axis, leaving the X axis to be free. Why should the X axis be free? Because we are going to need to apply an X axis deformation on that nodal set point too. Of course, if we just apply it, everything on that face will deform as well. So the next thing we need to do is apply the constraint equation that makes the linkage between what's happening at reference point 2 and the Y top nodal set. Then after that, we need to introduce a second boundary condition. This time around, we're going to hold the Y base of the system in the XZ plane. So if you study this carefully, what you will notice here is that the whole base here is going to be constrained with that end. So that means the line, this point of intersection, will actually be constrained in the X, Y, and Z direction. So this point will be fully constrained in the X, Y, Z direction, leaving this top section to be free to move in the Z x-axis and leaving this end to be free to move in the y-axis. So that way we are going to then have a deformation that runs this way, and this other one will deform this way. So that's how we are ending up achieving this XY in-plane shear deformation. Of course, to do that, we also need to apply a displacement in the y-axis at this reference point. And as well as that, we need to include the canonical equation that makes the linkage between the reference points together. Then for the YZ shear, a similar thing would have to happen. What we are looking for here, there will be a deformation in the Y direction and a deformation in Z direction to give you a YZ shear. So the boundary condition we need first is we need to fix the base so that it will now be free to move in the Y direction. So if you see, we are fixing it in the X and Z plane direction, so it's free to move in the Y direction due to this Y axis. And to do that, we need to introduce deformation like this. So in this case, we are pulling the system down. We could pull it up, but I just chose to pull it down. Okay, so if we're pulling it down, so that means it's free to move in the Z direction, sorry, in the X direction. Now, the next thing we need to do is to think about the Z axis. So again, we have to apply the canonical equation that forces this plane to be connected to the Z front face. Now, the next thing we need to do is to constrain the back end now. So with the back end, we are allowing it to move in the Z axis. So that means the X and Y is constrained. So if you look at this, if you consider what's happening here and here, so that means at this point, we are going to then have the system fully constrained in X, Y, and Z axis. So it will be permanently fixed, while this would move in the Z axis and while that will move in the Y axis. And then of course we need to introduce a displacement in the Z axis to now make up for what we are saying Y and Z. So this is the movement in Y, this is the movement in Z, and we need a canonical equation to connect the displacement of the X front set with respect to the reference point 1, and that's what we see for YZ. Finally, in the XZ direction, we've got our system again. We'll constrain the back end in the XY directions, leaving the Z plane to deform because we have a Z displacement involved here. Now, the next thing we introduce the loading on that direction and the relevant canonical equations that makes the displacement of the X front connected to the Z direction. Now, the next thing we need to do is to constrain the back end in the YZ plane. And looking at this system, at this point of intersection, you find again that the system is fully constrained in the X, Y, and Z direction, which means that every other thing around here would move in the Z direction and everything around here move in the X direction. So you end up with an XZ shear, pure shear deformation. And of course, the loading that will make that happen will be like that. So again, I chose this direction because I want the system to move away and that one will move away. So we end up having the system opening up like a fan. So of course, you can change the direction and you'll still get the result as well. So there will also be a corresponding canonical equation that makes the system to be connected, where the Z front face, which is this, is linked to the reference point 3, which is this. Okay, and then because we are looking at the x direction, so we're extracting what's happening in the x direction. So, and 1 talks about the direction of displacement. So that's how you set up the XZ shear. So with all that, we are going to then go and set this up with ABAQUS. If this is the kind of content that you like, please, I do encourage you to subscribe to this YouTube channel so that when contents like this are made, you'll be the first to see it. I also want to highlight that there is a CM Videos Insider group which I regularly send every week newsletters talking about behind the scenes in CM Videos and more about products that are available on the CM Videos website. I also publish in this newsletter reflections from my perspective on a lot of computational modeling issues. If you are interested in this kind of thing, please do subscribe to the newsletter. You'll also be able to read up to 100 articles already published on that newsletter. Thank you. For this video, we want to create the shear stress cases. So all we need to do here is create a copy. So our copy here will be BDXY shear. The first thing we need to do here is to apply the X back region. So X back is fixed in the YZ plane. So X back is fixed. So if we go back and look at the boundary condition, so our X back is fixed. So I'm going to rename that and then basically call that F back fixed, and it's fixed in the YZ direction, so Y and Z being free to move in the X direction. So YZ is how it is fixed. Then the next thing is we need to apply a load that node. So what do we do? So we create the load. So that would be the reference point 2 load in the X direction. Okay, reference point 2 load in the X direction. So that means we are applying it in those two directions and it's in the X direction. And because the system is 100, so we're looking at 10% strain on the system. So then the next thing we need to do is to apply the constraint equation for that. So what do we do? So again, I'm going to call it my reference point 2 constraint equation. Okay, so now what do we do? So we are looking at 1 and minus 1. So we are constraining the top face, Y top, in the one direction, the reference point 2 again in the one direction. So that's what we see here. So reference point 1 in Y top and 2 in the one direction. We've got a setup that looks correct, and then we work with that. So basically that node is connected to the top face and we're happy with that. So with that, the next thing we then look for is the Y base is fixed in the XZ plane. So Y base here, and it's fixed in the XZ plane. So we'll change this to an F to show fixed. And then if we look at that, so it's in the XZ plane, XZ plane. So we choose those two as how it is fixed. So XZ plane. And then the next thing we need to add there is a deformation in this reference point 1 and the y-axis. So what do we do? So we create that and we call it reference point 1 load in the y-axis. It's what we are looking for. And it's going to be on reference point 1, and we want to apply it in the y-axis, and that y-axis has got a unit of 100, so 10 would be what we need. So again, you have a load in that point that is active there. So we've got this load, we've got that load to represent the shear stress deformation, and so we've got all that. So the only thing that is not needed here is this bit, and we're going to suppress that. You can delete it or suppress that. So that's what we have. And then with that, we can look at our constraint equation for the second case, so which is reference point 1 constraint equation. Okay, so with reference point 1, again, we've got 1 minus 1, and now this time around we are looking at the X front face and we are linking it to what's happening at reference point 1, and we are moving it in the two directions. So you get XY, X, Y being what you have here. Then obviously we need the history output for those two. So we're going to get reference point 2 history output. So remember, reference point 2 history output. So we go and look at reference point 2, and it's moving in the one direction. So we're looking at reaction force 1 and U1. So that's what the loading is. So the system is being moved in one direction, and we're happy with that. So we create another history output, which is the reference point 1 history output. So with reference point 1, again, the set will be right. So we're looking at reference point 1, and we are moving it in the y-axis, which will be RF2 and U2. So that's the loading we have. So basically we are extracting the history output of reference point 1 as it deforms in y direction and reference point 2 as it deformed in the x direction. And so everything about the shear case is set up correctly, and we are ready to then submit the job and run and get our result. So our next shear case would be for BDYZ shear. So with the YZ shear, so we are going to impose a fixed base, y base, in the XZ plane. So with the y base, so we look at what we have here. So we've got y base, so I'll just rename that and then call it y base fixed. Okay, and we are going to fix it in the x and z direction as shown here. So what we're looking for, so we're going to then apply a load at reference point 3 in the y direction. So I'm going to call my loading here reference point 3 load y, and it will be a loading history. Okay, and it's going to be on reference point 3, and we're going to deform the system in the 2 direction. The next thing we need to do is to consider the constraint equation for that, and the constraint equation here would be the reference point 3 constraint equation. So what we are doing with the reference point is 1 in this point minus 1. The set name that we want is the Z front, and our P1 is what we are working with, and we are moving in the 2 direction. So that gives us ZY, or YZ, ZY in this case. So for the next set, what we want to do is the Z back fixed in the XY plane. So if you come back here, Z back, we are going to rename that. So that would be Z back fixed. And if we open that, it's in the XY plane, so X and Y, and we're going to untick this. So XY plane and Z back. So now it's constrained there, and so the only one that is remaining is the X back. We are going to suppress that so that we have what we need, which is the Y and Z, or both constrained. If we then go back here and look at this, so what we want is the reaction force in the third axis, and it's on reference point 1. So this will be reference point 1, load in the Z direction, load in the Z direction, and we're acting that on reference point 1, and it's acting obviously in the third axis. So no, it's in the third axis and it's 14, but we want it to be minus 14 because it's going to be pulling in the back direction. So if we look at it, so you can see it's pulling backwards like shown here. So like shown here, so it's pulling backward in the Z, in that Z direction. So again, we need to provide a constraint equation for that. So that's reference point 1 constraint, and again that will be 1 minus 1. The set we are looking at is the X front and reference point 1, and it's moving in the third axis. So with the XZ shear, the first thing is the Z back. So we look at the Z back. So I'm going to rename this Z back fixed, and with the Z back fixed, we are constraining in the X and Y direction. Okay, so Z back is fixed. Then the next thing we need to do is the reaction point 1 pulled in the Z direction. Reaction point 1 pulled in the Z direction. That's our load, and it's going to be an initial boundary condition, and that will be reaction point 1. And with that, we are pulling in the Z direction, and it will be minus 14. Then the next thing is we need to plug constraint equation. So reaction point 1 constraint. So we'll go and say, okay, this is reaction point 1 constraint, and it's an equation. So we have 1 and minus 1. The set name. So if you want to get the stress and stress data, then look at this video. Thank you for your interest in this, and I'll see you in the next video. Bye bye.